Okay. Is Cassie here?
Yeah, somewhere.
Okay. Well, we're doing 2 more days of notes and then review Wednesday, test Thursday. So today we're doing like one-on-one functions, which is introducing like inverse functions, which we'll spend more time on tomorrow. And then, yeah, that's where we're going. So before we could get into one-on-one functions, we should first remember what is a function, that we can talk about a one-on-one function. Anybody recall what a function is? Okay. So a function has to pass the vertical line test. Yep. So that's a true statement. What else do we know about a function? Okay. Yes, so every x value has exactly one y value. So that's like the definition of a function, which is basically what I wanted. And then the vertical line test, basically, if you're given like a graph, you can like do the pencil test, figure out does it pass the vertical line test. Okay. So most of the times we have like function notation, so we could write functions as f of x. If you ever see that symbol, then you know the graph of this function will pass the vertical line test, and it is a function automatically. Okay. So now that leads us into one-on-one functions. So basically, it's like the complete opposite of all of this stuff. So for it to be a one-on-one function, it has to pass the horizontal line test. Okay. And then instead of every x value has y value, we have every y value has exactly one x value. And when they talk about one-on-one functions, we're basically like assuming that it's already a function, so it's already every x value has one y value. Now we have to prove the opposite. Every y value has one x value. So basically, it's called one-to-one because every x has one y and every y has one x. Okay, so for it to be a one-to-one function, it has to pass the horizontal line test and the vertical line test, and everything has to be lined up. Okay, I'm gonna skip this. We would know horizontal line test is the same as vertical line test. It just determines whether it is a one-to-one function. Okay. So we have this guy, f of x equals the square root of 25 minus x squared. So basically how it's written, I already know it's a function because it's in function notation. So that's nice. But now I need to figure out, is it a one-to-one function, so does every y value have one x value? Or does it pass the horizontal line test if we think about it graphically? So does anybody know what the graph of this would look like? You would think. So that's what a square root function does. But since this is a squared underneath the square root, it's not quite. It's just like 25 minus x and yeah, just half of a parabola. So, 2 ways to do it. If you want to think about it as a graph, I would probably like rewrite this and we'll see if you know what it looks like after we rewrite it. Okay, so I just replaced f of x with y just because I'm going to manipulate this a little bit into something that we might know what it looks like. So basically I can square both sides to get rid of the square root. So I have y squared equals 25 minus x squared. And then I could add x squared to both sides. So if I wrote it like this, do we know what this looks like? Yeah. So if you have x squared and y squared, this is technically a circle. And specifically, since it started with a positive square root, it is like the top half of the circle. Technically. So, does it pass the horizontal line test if it's circled? Yes, so this is not 1-to-1. So they say if you want to do it an algebraic way, it's not really that much fun to think about it as an algebraic way. So basically they say you need to think of two x values that are different that would yield the same y value. So if I'm just looking at the f of x equals the square root of 25x minus x squared, then I think of two different x values that would give the same y value. So you kind of have to be like creative when you think about it. So if I was doing it, I see it's x squared at least. So that's going to get out the same x value for the positive and the negative x value. So if I plugged in like x equals 2, I get out f of x equals the square root of 25 minus 4, which is the square root of 21. Same if I did x equals negative 2, I'd still have the square root of 25 minus 4, which is the square root of 21. So that tells me it's not a 1-to-1 function because I have the same or two different x values for the same y value. So that's not as like visually friendly, I guess, to understand it. So that's how you do it in algebra. Okay, so there's that example. Here's a different one. So same thing, I want to figure out, is this a 1-to-1 function or not? So I guess if I could, I'd always think about it as a graph. So does anybody remember what the graph of this would look like? Yeah, it's a rational graph. So if it's ever just x to the first power, doesn't matter what the graph is. Does anybody know what the vertical asymptote is actually? -3. Right, so I could draw that in, but then the rational function will be like this. So does this pass the horizontal line? That's what you want. Right, so even though it looks like it starts to approach horizontally, it is still decreasing like just minusculely, right? So it's still going to pass horizontal line test even though it appears horizontal at the end. Okay, so this is also a 1-to-1 function. Okay, so moving on to inverse functions. Does anybody remember what an inverse function is? Or what does inverse actually mean? Yeah, I always think of it as unuse or like opposite. Right, so we have like inverse of addition, which is subtraction. Inverse of multiplication is division. Inverse of a square is a square root. Okay, but I could find like inverse functions, which basically like undoes all the operations. So we'll talk about inverse functions more tomorrow on how to find inverse functions, but we can verify that a function is its inverse. So to verify, we have to do the composition of f and g. So we're assuming like f of x is a function, g of x would probably be the inverse that you would do it with. If you compose them, you should just get out the variable x and nothing else. So if you compose it, all the operations cancel each other out. And you have to prove the other side, so you have to go the opposite way. So the g composed with f of x also should just get out x. So does anybody remember how to compose functions? Right, you would rewrite it as f of g of x. So you substitute g of x in the f of x function. Same thing with g of f of x. So this is the only piece of inverse functions that we're actually doing today. So this guy, we're just given like a set of ordered pairs, which they could represent functions. We want to figure out if they're inverses of each other. So we'll see. We remember another piece of information about inverses. Okay. So the function f, I have the ordered pair 1, 2, 2, 3, 3, 4. Function g has ordered pair 2, 1, 3, 2, and 4, 3. So if I was just looking at it, looking at just the function f, I know it's a function because every x value has one y value. I know it's a 1, 1 function because every y value has a different x value. Same thing if I look at g of x, it's a function because every x value has a different y value. Every y value has a different x value. Okay? But I want to know if they actually are inverses of each other. So does anybody notice anything about f and g? Yeah, so like the order pairs kind of flip-flop. So when they flip-flop like that, technically that is an inverse. Tomorrow when we start finding inverses, you interchange the x and y value. So if you're looking at order pairs, technically this is, yes, inverses. Super fun. Those are easy, just look at it. So verifying by doing composition, I picked the hardest one with rational functions. Just because. So this one's difficult just because it is rational functions, and you have to remember how to work with fractions, and simplify fractions, and do all the things. And it gets all sorts of messy looking. Okay. So if I'm looking at it, we know inverses, they have to have like opposite operations. So like f has a +1, g has -1, so that like looks fairly okay. This one has a -2, this one doesn't. So just by looking at it, I would assume that these are not inverses of each other. But we need to mathematically show that by doing composition. Okay, so maybe we just start with like f composed with g of x and see how far we go down. So remember, I can have f of the g of x function 2x plus 1 over x minus 1. So then g of x, that fraction is going into every x value in the f function. So we're going to have like fractions and fractions, and it's going to look weird. So instead of x plus 1, I have a fraction, 2x plus 1 over x minus 1 plus 1. And then over the same thing. Okay, so basically plugging in g of x into f of x, and this is what I get out. I need to simplify this down as much as possible. So does anybody know how to simplify when there's a fraction, a huge fraction like this? Okay, so we can multiply the top and the bottom by my denominator, which is x minus 1. So I'm looking at the tiny fractions. I want to get rid of a fraction in the fraction type of situation. So I can multiply the same thing on top and bottom, taking splits out. So I'm technically multiplying by like a 1. So then when I distribute it in, x minus 1 times this fraction would cancel, so I'm just left with 2x plus 1. But then I have to multiply x minus 1 to this 1. So then you like distribute a 1 inside. So we have 2x plus 1, and then plus x minus 1. So that's my numerator now without that fraction. Same thing, distribute x minus 1 to that fraction, the denominator would cancel with it. So you just have 2x plus 1. And I'm just going to distribute negative 2 to x minus 1. So it'll be minus 2x, and then plus 2. And then we can simplify in final terms and do all the things. Well, hey, look at that. So I got out x. So that side is composed. This is telling me it is an inverse, but I need to check the other side because the other side might not check out either. So I always have to do both sides. So going the opposite way, g of f of x. So same thing, we're just plugging in f of x into the g function. I guess before I would cancel out the denominators like we started, I would distribute that too, so I wouldn't have parentheses first. So it won't mess me up later. So when you have the 2 in front, write it as 2 over 1, so you just multiply the 2 to the numerator. So 2x plus 2 over x minus 2. So right now my denominator is x minus 2, and that's what we're going to multiply to the top and bottom, just like we did before, and we're going to distribute it out and cancel. So the x minus 2 cancels for the first term. I just have 2x plus 2. And then we can multiply 1 to x minus 2. Same thing in the denominator. X minus 2 is canceled, and we just have x plus 1. And then distribute negative 1 to x minus 2, get negative x plus 2. So then putting my terms and dividing, we get x. Okay, so my initial assumption was wrong. So since they both simplified down to x, these are inverses. Can't see that. Okay, so that is what we're doing today. Make sure you do D4, not even. Bad.